So one of the ways that you can test whether a graph is a function is to use a vertical line test. And what that means is if the vertical line can pass through exactly one point, right? So in a function, each input has exactly one output. So if you draw a vertical line anywhere on the graph, if it passes through the function or the graph in more than one place, it's not a function. So here we have a continuous graph. There's no place on this that we can pass a vertical line and intersect that graph in two places or more than one place. So yes, this is a function. Here, same thing. As we draw in vertical lines, there's no place that a vertical line will pass through the graph in two spots. So yes, that is also a function. Notice here, there's a lot of different places where a single vertical line will pass through the graph in two places. So no, not a function. Again, you see it passes through more than one time, so no, not a function. Here, this is absolute value, so yes, again, it passes the vertical line test. A linear function passes the vertical line test. A perfectly straight line is not does not pass the test. It's not a function. It's a constant. And then here again, we can see there's multiple places on that graph that the vertical line would pass through. So that would also be a no. So if you're being asked to identify functions, that's an easy way to do it visually. And there are some specific functions called toolkit functions. We'll also kind of refer to them sometimes as parent functions that are just the most basic form of a function with no transformations. And so this is something that you should recognize the forms for. So if we take a closer look at these, a constant is just a horizontal line passing through whatever the y coordinate is. In this case, it's a 2. So that is a constant function. If you look at an identity is a linear function. Oops. So the basic no transformations is just this equation y equals x. Okay? Again, this would be y equals b some constant. Absolute value is a V-shape graph. Again, if you see a graph like this, you know it's an absolute value. Quadratic function is a parabola, and so a parabola is just a U-shaped graph. For a cubic function, it's going to have an S, kind of a curve down and to the left, up and to the right. So that is a cubic function. A square root function looks like this. It begins at the origin and extends. A cube root function has the S curve. A reciprocal function has a vertical asymptote, has a horizontal asymptote. We'll have shifting rules for those later, but just the parent function itself looks like this. And then a reciprocal square has the same rules for the asymptotes, but this time both parts of that function or both sides of it are going to give you positive outputs, and so this is your reciprocal squared function. So those are the different functions that you need to be familiar with when you recognize them or when you sketch them. And we'll use transformation rules to just slide these up, down, left, right, stretch them and shrink them and reflect them. Right. Again, continuing to talk about the graphs of functions, what you need to be able to do is identify and evaluate functions. If you know that f of x has an output of some value, some number 1, okay, we'll call it b for right now, then you can rewrite this as an ordered pair where your input of x gives you an output of b. Now, if instead of that you have an input of some number is your input, and you know what your corresponding output is, once again, It's the same rules. The input A gives you an output of Y. And so you can kind of use these rules here to work back and forth between function notation and the points on a graph as an ordered pair. And what that allows us to do is it allows us to look at something like this. And it says you want to find what x values would give you an output of 1. Well, here's our 1 right here. So if we follow on this graph the two places where we have an output of 1, what you're going to see is it's here at this point -2, 1, and out here at this input of 6, 1. And so those are the two x coordinates just by looking at the graph that give you the designated output of 1. The next one is this second scenario where you're evaluating the function based on a graph. So here again we're looking at an input of -2, and if we find where that is on our graph and look what's the corresponding y value at that point, it is 2, -1. And so the output when our input is a -2 gives us our value here, which we saw to be -1. So again, this is something that you need to be able to see just by looking at a function. All right, there's a couple things in 3.6. We'll talk about one of them here in this part, and then in the next part we'll talk about the other. But when you're in AP Pre-Calc, one of the hardest things that students have found is discriminating against where a function's increasing and decreasing versus where its rate of change is increasing and decreasing. So notice the slight difference in how I'm describing that. If you have a graph that is increasing, the function itself, what that means is that as x gets bigger, so does y. Okay? A decreasing graph is the opposite. As x gets bigger, y gets smaller. And so when you're looking at the function itself, like this is how you're gauging those differences. Okay, so another way to put it is that in the interval from a to b in a function, if f of a is always less than f of b, then you're dealing with an increasing graph. That means it's always going up and to the right. If you're looking at the decreasing function, then in that same interval, on the interval from a to b, in this case now the functions when you evaluate the function for a, it's always going to be greater than if you evaluate the function for b. So again, you can kind of use some either visual cues, which are probably the easiest to use, but there's also an explanation for it sort of along the interval notation of mathematics. So let's take a look at what we see in these examples here. Okay, if you want to determine for each of these graphs right here, which of the following or what are we dealing with involving increasing and decreasing. So when we look at this blue graph, it's going down and to the right. Down and to the right means it's decreasing. Whereas this red graph right here is going up and to the right, so this graph is increasing. Here, again, when you're looking at, so that's a linear function, it's always going to increase or always going to decrease. Sometimes functions change directions and have portions that increase and portions that decrease. So if we look at a quadratic function, what we see is in these two sketches here, these yellow highlighted pieces are the parts of the graph that are increasing. They're going up and to the right. But if we look at the portion of the graphs that are going down as you move to the right, now we see the portions that are decreasing. So here this interval, the interval that's highlighted green, is the decreasing part of that graph. Where they change directions, it's a constant, it's that instantaneous, no, it's not increasing or decreasing. It's in that sort of limbo state of changing from those. So if we go back to this polynomial function here and we look, what we can find is that the increasing parts, here the graph's going up and to the right, up and to the right. And here in green, we see the graphs going down and to the right, down and to the right. So those are the different portions. We have decreasing, then increasing, then decreasing, then increasing. Okay, so when you're looking at the functions themselves, again, the graphs, the increasing or decreasing functions, when you're describing it in that sense, it's just asking, is the graph going up and to the right, or is the graph going down and to the right? So you can also be asked to do the same thing just by looking directly at an equation. And this involves just knowing what the parent function looks like or what the general rules are. So for a function like this, the y value is always the same, just a flat graph at y equals 6. So this is neither. This is a constant. It's neither increasing nor decreasing. Next, we have a positive slope. Again, for a linear function, we simply need to know, is the slope positive? If it's a positive slope, then it's going to be increasing. Here we see another positive slope in this linear equation, so that's also increasing. And then finally here, if we wrote it in the mx plus b form, we have a negative slope, so this final example, the graph will be decreasing. Okay, so again, like when you are looking at this, you can try to find where those portions of the graph occur. And so when you are looking at this part here, it's asking you, of the following intervals, which intervals is f decreasing and the graph concave up? So we'll come back to this here after we look at the next slide. We'll return to this in a second because we haven't talked about concavity yet. So let's do that. So concavity has to do with whether a graph is concave up, so whether it curves up like a smile, or concave down, where it curves down like a frown. Right? And so when you're looking at these, one of the ways that we're going to kind of introduce concavity has to do with how the slopes are changing, okay? Or the rates of change are changing themselves. Okay? And so when we look at this, one of the things we'll find in the next set of notes is talking about how the rate of change is a tangent line. So if you wanted to find the rate of change at any point here on this graph, you would draw a tangent line through that point. You could do the same thing here on the upward portion. So notice in this concave up version, the tangent that represents the slope of that graph is always below the given function. Okay, so here the tangent is below the graph itself. Now, if we look at the cases where we have a concave down function, at this point, here's our tangent line. That gives you the slope of the graph at that point. Here's another instance where it gives you the slope of that. And what you can see for a concave portion of a graph that's concave down, the tangent is always above the actual graph. So that's one way that you can, again, kind of mathematically see when is a graph concave up or concave down, and it has to do with the tangent being below for concave up and above for concave down. Now, the part that winds up being a little more challenging for students to see is this idea that when the graph is concave up, the rate of change, which is the slope at any given point, is always increasing. Now, this doesn't mean that the graph is always going up and to the right. It's not that the graph isn't increasing, it's the rate of change is increasing. And that means it's either getting less negative, which is the case here on the left side of this graph. What we see is as we come down here, our slope is getting steep and negative, but here it's starting to get less negative until it's 0. Right at 0, it then starts to get more positive. So it's less negative or more positive over that when you're dealing with a concave up portion of a graph. Now, compare that to concave down. So notice here that this part of the graph is very steep and positive. Here it's getting less and less positive. That means that the rate of change is now decreasing. Again, it doesn't mean that the graph is decreasing, because in that portion right there, the graph is actually increasing. But if it's concave down, the rate of change is actually decreasing. And that means, again, that here we see it's getting less positive. And here, when we get on the other side of it, now it's flat and the instantaneous slope is 0. But as you start to go to the right of this on that concave down, it now gets more and more negative. So it's less positive or more negative, and that happens as the rate of change is decreasing. It's getting more negative as you rotate this. So think about like a dial. If you're looking at a dial here, and you take this dial and you rotate it, that's getting more negative. Here, if you look at this dial and you're rotating it, here you're getting more positive. And so if you kind of think about like the dial turning it down, you form this concave down portion, and here you're forming this concave up portion as you turn it more positive. Again, this is a concept that is really challenging for students to see. But if you just kind of sketch what you have, and you see here when it's concave up, we see that our graph is steep and negative, less negative, less negative till it's 0. So very negative, now it's 0, and now it's getting positive. So as you move here, this is getting more positive or less negative. Looking at the concave down, when you're identifying this, again, as you start here, it's positive, but it's getting less and less positive. At this point up here where it changes directions, it's at 0, and now it's getting more and more negative. So again, what you see is as you go from left to right, it's less and less positive, and it's getting more and more negative. So again, hopefully you can kind of visualize that as you're being asked these questions. So the other relationship that you see here is when a graph goes from being here concave down to here concave up, it happens at this point called an inflection point. So the inflection point is the point where a graph changes concavity. Okay, and right at that inflection point, again, what you see is it's going from concave down to concave up. Okay? So that's called an inflection point. And a lot of times what you're going to be asked to do is to sort of eyeball it. When you're looking at this example right here, what you see is the graph is from here to this point right here, it's decreasing. Right? So we know that from negative infinity to b, it's decreasing. We also see from d to infinity, it's decreasing as well. So we can look at that portion of the graph. We see that this portion from b all the way to d, that is increasing. That's going up and to the right. So again, that's not talking about the rate of change. That's talking about the function itself, is increasing or decreasing. Okay, we can see where the graph intersects the x-axis. Those are the zeros. So at A and D, we have intersection points or zeros. Now it's asking us to determine where is this graph concave up and concave down. Well, what we see is the graph is concave up from here to somewhere between B and D. It changes from being concave up to being concave down. And so if you kind of eyeball this, that looks to happen right at point C. So we can find that. If you're being asked to locate it with a number, give your best guess. There's going to be some tolerance level that allows you to make some guesses or be close to it. But what we see is that we're concave up all the way to point C. So from negative infinity to B, that's concave up. B to C is also concave up, but there's nothing in no other interval from B to C. So really it's from negative infinity to C is the concave up. So that's the portion of it from the options. Concave down is going to go from C to infinity. Again, what we see here is that answer is included in this problem. Right, so if we return to the previous slide to talk about the increasing in concavity. So what this question is asking is what part of the function is decreasing and concave up. Okay, so let's look first where it's decreasing. From A to C is decreasing, and then from E to G is decreasing. And let's look as well, like what part is concave up. When you're looking for the portion that is concave up here, right to this point is your concave up, and then it switches to concave down. And so what we're looking for as our answer is on which part of the interval is f decreasing and it's concave up. The only place where that's happening is from A to C. So from A to B it's happening, and B to C, so it's over those two given intervals, and that you see the graph is decreasing and concave up.